Assalamu alaikum dear students. Today we are going to discuss modulus and conjugate of complex number. Now let z equals to a plus iota b be a complex number. This means that the real part of this complex number is a, means real part of z is a, while as its imaginary part, that is of z, is b. Now if this is a given complex number, then the modulus of this z is denoted by mod of z, and it is non-zero real number and is defined as mod of z equals to root of a square plus b square, a square plus b square, while conjugate of this complex number is denoted by z bar and is defined as z bar equals to a minus iota b. That is simply change, or we are changing the sign of imaginary part. When we change the sign of an imaginary part of a given complex number, we get it is conjugate complex number. Here this mod z is not the uh, mod of z is not the same as for the real numbers, because for real numbers, if a is real, mod a is always greater or equals to 0. But here this denotes the root a square plus b square. It is non-zero real number. Like if we consider z equals to 5 plus iota 2, its real part is a, imaginary part is b, mod z equals root 5 square plus 2 square, which is simply root 29, while as its conjugate, that is z bar, is 5 minus iota b, 5 minus iota b. If we have z equals to 2 minus iota 3, then its a is 2, b is minus 3, mod z is root z square, a is this 2 square plus minus 3 square, that is 4 plus 9, so 13. Hence root 13 is the modulus for this function, while as its conjugate is z bar, which is 2 plus iota 3, because here for this complex number minus 3 is imaginary part, so when we change its sign, it becomes plus 3 iota. So here 2 plus iota 3 is this conjugate for, or is conjugate of 2 minus iota 3. Now if we consider z equals to 2, then this is the complex number. Its real part is 2 and its imaginary part is 0, that is 2 plus iota 0, because a is 2, b is 0. Mod z is root 2 square plus 0 square, which is simply root 4. Root 4 is 2. Now what is z bar? That is modulus, and this conjugate is obtained by changing the sign of this imaginary part. Imaginary part is 0, that is minus 0, hence which is simply 2, From this we conclude that for purely real complex number is that number where b is 0, that is imaginary part is 0, z bar is always z, that is conjugate as well as complex numbers are identical. Now if we consider z equals to iota 5, this is purely imaginary complex number. We can write this as 0 plus iota 5. Here a is 0, b is 5, so its modulus is this root a square plus b square, which is root 25, while as it is z bar, that is 0 minus iota b, that is simply minus iota 5. Now iota 5 is z minus z, so z bar is this minus z. So for purely imaginary complex numbers, z bar is always minus z, Now if we consider a complex number z equals to a plus iota b, then its modulus is root a square plus b square. If we squaring this equation from both sides, it is mod z square equals to a square plus b square, Also z bar equals to, for this complex number, z bar equals to a minus iota b, Now 1 upon z is 1 upon a plus iota b. Now we are going to rationalize this, because we have to convert this 1 upon z into form of a plus b that is a minus iota b upon a minus iota b, which is a minus iota b upon, here we have in denominator a plus iota b into a minus iota b, that is a square minus b square, which is a square plus b square, because we have here minus iota b square. Iota square is minus 1, that is plus 1, which implies that 1 upon z is a minus iota b upon a square plus b square. Now from here, a minus iota b is z bar, this is z bar, while as a square plus b square is mod z square, mod z square, which implies that 1 upon z is z bar upon 1 upon z, this mod z square. By cross multiplication, it is z into z bar is mod z square. So remember one thing, z into z bar is mod z square. So product of complex number with its conjugate is always equals to the square of its modulus, square of its modulus. Now if we have two complex numbers z1 and z2, you can easily verify that product of modulus, that is mod of z1 into z2, is product of the individual modulus, that is mod z1 into mod z2, while as quotient, if z2 is not equals to 0, this z1 upon z2 modulus equals to mod of z1 upon mod of z2, mod of z2. Similarly, z1 into z2 bar equals to, that is bar equals to z1 bar into z2 bar, while as z1 plus minus z2 whole bar is z1 bar plus minus z2 whole bar, and z1 upon z2 whole bar equals to z1 bar upon z2 bar. Now another question is, we have to find the multiplicative inverse of z by the modulus and its conjugate. You can find the multiplicate this modulus, this multiplicative inverse of any complex number by rationalization. Now today here we are going to discuss how to find the same through modulus and its conjugate. The given complex number is 5 plus iota 2. Its modulus is root 5 square plus 2 square, that is root 29, and z bar is 5 minus iota 2. We know that, we proved earlier that z into z bar is 1 upon z whole square, z bar whole square, which implies that z bar upon 1 upon z, this modulus z square is 1 upon z. Here 1 upon z is this 1 upon z is multiplicative inverse of this z. Here 1 upon z is z bar is here 5 minus 2 iota, while as its mod z square or mod z is root 29, mod z square is simply 29, which implies that 1 upon z, which is inverse, multiplicative inverse, which is usually denoted by z raised to minus 1, is 5 by 29 minus iota and iota 2 by 29. So in this way you can find the multiplicative inverse of any complex number, or you can find the modulus and this modulus and conjugate of any complex number. Only one number, that is if we consider zero complex number whose real part is 0, imaginary part is 0, modulus is 0, otherwise it is always non-zero real number. Inshallah, in tomorrow's video lecture we will discuss the polar representation and the organ plan, or the complex, simply a complex plan, and I will in that lecture we will discuss the geometrical representation or geometrical meaning of this modulus and conjugate of a complex number. So thank you.